Hello, dear students. This is the next chapter, Laser, which is from your paper, Classical and Modern Optics. We have done a portion of this chapter during our contact classes, and in these videos, the following videos, I will be covering the leftover portions. And this is lecture 1 in Laser. The content of these chapters include the basic principles of laser, the Einstein's coefficients, the working theory of the laser, the line broadening mechanism and line shape functions. We will learn about different types of laser and different examples of laser, and also about applications and characteristics of lasers. By the end of the chapter, you also have to learn some of the non-linear optics. During our contact classes, we have learned about the basic principles of lasers, the Einstein's coefficients, and working theory on how a laser works and its diagram, a block diagram of how a laser works and what are its essential components. During our contact classes, we have started learning about line broadening mechanisms and also about line shape functions, but we couldn't finish this. So today in this lecture, this video, I will be talking about the broadening and line shape functions. Just to give you a recap of what we have done during our contact classes, Laser is the abbreviated form for light amplification by stimulated emission of radiation. That is, some light which is given to the medium is being amplified, and this is done with the help of stimulated emission of radiation. Electromagnetic interaction with the electromagnetic waves can interact with an atom by different ways. It can contribute to stimulated emission, it can cause spontaneous emission, and it can cause stimulated absorption. When a photon interacts with a ground state electron and it absorbs the photon energy and goes to a higher state, then it is called stimulated absorption. When a photon in a higher energy states when an electron in a higher energy state emit a photon after completing its lifetime and coming back to the ground state, then it is called spontaneous emission. In the case of stimulated emission, an electron which is in a higher state, which have not completed its lifetime in that state, is being interacted by another photon which have a frequency which is competent with the energy gap, will interact with that electron, and that electron is being scattered and it comes to the ground state by emitting another photon, and this case is stimulated emission. Therefore, laser works by the principle of stimulated emission. We have also looked into Einstein's coefficients for all these, the stimulated emission, spontaneous emission, and stimulated absorption. Both the stimulated emission and stimulated absorption was given B12 and B21 coefficients respectively, and the stimulated absorption had a coefficient A21. Under thermal equilibrium, the electrons which goes to a higher energy state absorbs energy and going to a higher energy state, and the electrons which are coming down to the ground energy state will be in equilibrium. That means B12 into N1, which N1 into U of omega, that is probability of going into a higher state, will be equal to probability of coming down to a ground state. Probability of going into a higher state, which is only by stimulated absorption, and probability of coming down to the ground state can be due to spontaneous emission or stimulated emission. Therefore, all these probabilities will be equal when under thermal equilibrium. So, we can write B12 N1 U of omega is equal to A21 N2 plus B21 N2 U of omega, where N1 and N2 are the number of electrons in the ground state and in the excited state respectively, and U of omega is the input energy intensity, the intensity of the photon which is being pumped into. And we have calculated that the stimulated emission by stimulated absorption will be equal to N2 by N1, because during derivation we have found that B12 will become B21 at thermal equilibrium. Therefore, at thermal equilibrium, stimulated emission by stimulated absorption will be equal to N2 by N1. But under normal conditions, we know that N1, that is the number of electrons in the ground state, will be much higher than the number of electrons in the excited state, that is N2. Therefore, under normal conditions, stimulated absorption will be dominated over stimulated emission. But for a good working laser, we need stimulated emission to be dominant than stimulated absorption. So we will look into mechanism so as we can reverse such that N2 is greater than N1. That is, at some minimum time, if we can make the population in the higher energy state higher than that in the ground state, then we can gain stimulated emission, and thus we can make a laser work. So for a laser to work, the laser medium particles should have at least 3 energy state, that is a ground energy state, a metastable state, and an excited state. An excited state will have a very short time period, lifetime, maybe of the order of 10 to the power negative 8 seconds. A metastable state will have a time period which is comparatively higher, that is 10 to the power negative 3 seconds. And the ground state will have a much higher lifetime. During pumping, the laser works in 3 different steps, that is pumping, population inversion, and lasing. During pumping, we introduce some photons. We give energy in the form of electrical radiation or in kind of light radiation or some thermal energy. Some kind of energy is given to the atom, and inside the atom the electrons which are resting in the ground state absorb this energy and go to an excited state. Here the excited state is very short period, so the electrons cannot stay there for a longer time. They will spontaneously decay to a metastable state. The decay from excited state to the metastable state is spontaneous and also is non-radiative. That is, it doesn't emit any kind of photon during this spontaneous emission. And in the metastable state, all the electrons will accumulate because the metastable state has a higher time period. The electrons will accumulate. At some point, the electrons at this metastable state will become higher than the electrons that is at the ground state. That is, at some time during this, N2 will become greater than N1. And this point is called population inversion. Therefore, population inversion is a time period, it's a phenomenon when which the number of electrons in a higher state is greater than the number of electrons in the ground state. So we achieve population inversion through pumping. And after achieving population inversion, some of the electrons which have already accumulated in the metastable state will complete its life period and will spontaneously emit radiation which is a radiative emission. It will spontaneously emit radiation and come to the ground state. And these photons will have an energy equal to h nu, that will be equal to the energy difference between the ground state and the metastable state. And these spontaneously emitted photons will resonate back and through the laser medium, and which will cause stimulated emission of all other electrons which are accumulated in the metastable state. This will disturb the equilibrium of every electrons which is accumulated in the metastable state, and those electrons will emit stimulatedly, that cause stimulated emission, and all electrons will come down at the same period, giving coherent radiation. And this coherent radiation, which is of the same energy and at same phase, will give us laser. And this process of stimulated emission is called lasing. Therefore, the laser works by pumping, population inversion, and lasing. To achieve a lasing, we need to have some laser arrangement such that a laser contains a gain medium. A gain medium is a medium which contains the laser material, that is the atom which can provide a 3-level energy state, at least 3-level energy state. It contains of an energy source or a pump. It can be an electrical discharge, or it can be a photon, light discharge, or anything, heat discharge, or any source of energy which is used to pump and achieve population inversion. It will have two mirrors. And one of the mirror will be a total reflector, and one mirror will be a partial reflector. The partial reflector will reflect the laser, and by the time it also gives out some laser beams, and laser beams comes out of this partially reflecting mirror. To achieve good lasing, the laser photons, which the laser, as I've already said, when the electrons complete its time period in the metastable state, it will spontaneously emit to the ground state, and these photons will reflect back and forth between these two reflectors, and during its journey between these reflectors, it will stimulate all other electrons in the metastable state and stimulate them to emit coherently and cause stimulated emission. Therefore, these photons which are emitted spontaneously or stimulatedly have to reflect back and forth between these mirrors. For a good laser, this reflection between these two reflectors have to form a steady state, or have to form a wave which is a steady wave. Therefore, to achieve this, we need to fix the length of the laser medium or the active region as 2L is equal to n lambda, where lambda is the wavelength of the emitted radiation. Therefore, twice the length of the laser medium or the active region, that is region between the two reflectors, have to be equal to n times lambda, where n is an integer. That is, the phase difference between them have to be 4 pi. That means there should be no phase difference between the reflected waves. That is, they must form a standing wave inside the medium. Then only we can get coherent radiation. From this, we have calculated the resonant frequency Fr as Fr is equal to Nc by 2L, where c is the velocity of the light in the medium. We have also learned about the Q factor. The Q factor is the energy stored in the medium. divided by energy lost in the medium during one cycle. So a good laser will have a good Q factor. Q factor is the ratio of energy stored by energy lost in one cycle. That is one time when it is reflected back and forth in the two reflectors. Now, in this video, we will learn about line broadening mechanism. In our class, we have started learning about line broadening mechanism. I will start over from here. So, in laser, we have just talked about laser energy levels. So, in a good laser, we should have at least 3 energy levels. So far we have considered energy levels to be single lines or single energy valued. Therefore, we will have only one radiation. One particular frequency radiation will only be there, and this particular radiation, say h nu, this particular radiation h nu will be exactly equal to the energy gap Eg between these two levels. But in all the cases, the energy level is not just a single line, but it is an energy band. This comes from the uncertainty principle. From uncertainty principle, we know that delta E into delta T will be greater than H cross. That is, if delta T is the time spent in one level, is delta T, and delta E is the uncertainty in determining the energy. So when the time spent in one energy level is lower, then the delta E, that is uncertainty in determining the energy of that level, will be very high. That is, when a level have a very less time period, then it will have a higher delta E, that it will have a higher band of energy. So having this band of energy actually gives us a lot of radiation. That is, radiation from this band can happen from this point, or it can happen from the middle of the point, or it can happen from the topmost. There are many infinite possibilities of having radiation emitted from the energy level E2 to E1. Therefore, in this case, we do not expect one single line in our spectral energy, because all the intermediate energy levels are possible. Therefore, our spectrum, instead of giving one single line, will give you a series of lines. That is, you can expect radiation at at frequencies which are higher as well as lower than the energy omega 0 which is expected. And this line broadening is called natural line broadening, because this comes out for every atom. This is true for every atom, and this is natural broadening, and this is happening by virtue of uncertainty principle, and this broadening cannot be avoided. The function which is plotting the energy of radiation versus the frequency omega are called line shape functions. There are mainly two types of line broadening, that is homogeneous broadening and inhomogeneous broadening. In homogeneous broadening, all atoms in the medium, so far we were talking about just one atom, but the medium will have several atoms. We can't just take one atom as a laser medium. The medium will have several atoms. In homogeneous broadening, all the atoms will undergo broadening in the same frequency region. That is, all the broadening will overlap and the end frequency broadening will be similar to any one of the atoms, and this is called homogeneous broadening. But in the case of inhomogeneous broadening, all atoms will have broadening in different frequency regions. That is, one atom may have broadening of say 2 hertz of width, and another may have 2.5 and so on. Therefore, many atoms will have broadening at different regions of the spectrum. So they cannot overlap together. So their region, that is the total broadening which we get from the spectrum, will be a combination of individual broadening, and such broadening are called non-homogeneous broadening. Now we will look into several line broadening mechanisms. There are several reasons for line broadening. We will discuss only 3 here, that are natural broadening, collision broadening, and Doppler broadening. We have already discussed about natural broadening. Natural broadening emerges because of the uncertainty principle, and it is a reality for every atom in the universe, and it cannot be avoided, and it exists. Collision broadening is due to collision of atoms between each other and also between the walls of the container. The Doppler broadening is because of moving of atoms towards the observer or away from the observer. This is a relativistic effect, and these 3 broadening mechanisms we will discuss in detail. Natural broadening happens due to the by virtue of the uncertainty principle. From uncertainty principle, we know that delta E, that is uncertainty in determining the value of E, into delta T, that is uncertainty in determining the value of time, or can be the time period which is spent in one particular level, will be less than or equal to h cross. Greater than or equal to h cross. And natural broadening is true for every case, and the line shape function for natural broadening we will get as this. Natural broadening is a homogeneous broadening, and we have already discussed this diagram. That is, in natural broadening, instead of one particular line dropping from a level to another level, we can expect a number of lines dropping from different sub-energy levels which is possible in one energy level towards the ground state. Therefore, instead of getting one particular peak, we will get a number of peaks which will peak exactly at omega 0, which was exactly the energy difference between E1 and E2, and all these separation broadening which came from natural broadening. So, if we have only one level, and this level, the broadening delta omega, that is uncertainty in determining the nu, the delta nu or delta omega, that is the change, the broadening which has happened in the region, can be calculated as delta nu is equal to 1 by 2 pi into t, where t is the time period of that particular energy level. From this equation, you can see that as the t increases, the delta nu decreases. Therefore, now we doesn't have one energy level which is being broadened. Every energy level is broadened. Every energy level is broadened, and the broadening goes higher. To the higher energy states, the broadening are much greater. Therefore, if nu1 and nu2 or delta nu1 and delta nu2 are the broadening, that is energy frequency difference due to broadening at energy levels E2 and E1 respectively, then the total broadening delta nu will be the sum of these two levels. Natural broadening is an example for homogeneous broadening. That is, every atom will undergo broadening in the same region. That is, delta nu will be same for all the atoms, and also the omega 0 will be same for all the atoms. Now, collision broadening. The atoms in the gain medium are under constant collision with each other and also with the walls of the walls of the container. Therefore, when an atom emits a photon while colliding, the photon phase will be changed and it will acquire a momentum which is lost or gained during the collision also. That is, the change in the frequency will be resulted, there will be a change of frequency which is resulting from the collision also. Therefore, change in frequency is not just coming from the natural broadening, it can also come from the fact that these atoms are under constant collisions, and these constant collision will impart some kind of a momentum into those photons which is being emitted, and this will dephases the wave train. That is, instead of getting standing waves of the particular frequency, the phase of a wave train can be disturbed due to collision broadening. Collision broadening is also an example for homogeneous broadening because the probability of colliding is same for every atom. Therefore, every atom will undergo the same level of broadening in the same region. Therefore, collision broadening is also homogeneous broadening. The change in the frequency due to collision broadening, delta omega, will be equal to 2 by T0, where tau 0 is a mean time between collisions. That is, as the mean time between collisions decreases, that is, when the collision have a higher frequency, then the frequency broadening, the collision broadening will be higher. Therefore, delta omega is inversely proportional to the time between the collisions. The last kind of broadening is Doppler broadening. Doppler broadening is due to Doppler effect. Hope you remember what is Doppler effect. Let me give you a recap. That is, when a light is traveling towards an observer, then when a light source is traveling towards an observer, then the observer will get light as with a higher frequency than it is being emitted. That is, the wave train before the source and the observer will be compressed, and thus the frequency of the wave train will increase, and thus the observer will receive a higher frequency wave. While a wave is moving away from a source, the light source is moving away from an observer, the wave train between the light and the observer will get elongated, and this will result in a lower frequency. Therefore, when a source is moving towards an observer, the observer will observe a higher frequency light, and when the wave source is moving away from an observer, the observer will observe a lower frequency. This phenomenon of observing a higher frequency is known as blue shift, and observing a lower frequency is known as redshift. This same case can happen inside a laser medium also, because the lights or the sources, the light source here, that are atoms, are moving inside. They are not stationary, they are moving constantly, so that they can move towards the observer or away from the observer. Therefore, the photon emitted will undergo redshift or blue shift, determined by the motion of the atom, and this will also result in broadening, and this broadening is known as Doppler broadening. Atoms will have a high thermal velocity, and the Doppler broadening delta W is calculated as delta W is calculated, omega is calculated as omega 21, that is the wave without Doppler broadening, into root over T by m, where T is the temperature and m is the mass of the atom. That is, you can see, as temperature increases, the thermal velocity of the particle increases and the Doppler broadening will be high. And also, as the mass decreases, the Doppler broadening will be high, because the less mass atoms will move much faster. Doppler broadening is a relativistic effect, and this is a non-homogeneous broadening. The Doppler broadening is an example for non-homogeneous broadening, because this will be different for different atoms. From experimental results, we can find that Doppler broadening is much higher than natural broadening, which is again much higher than collision broadening. Therefore, Doppler broadening will be dominant. The natural broadening, which is similar for every atom, and collision broadening is also homogeneous broadening. This is also similar for every atom. Under high pressure, collision broadening can become highly predominant, because under high pressure collisions will be much higher, and thus collision broadening can dominate under high pressure. But under natural conditions, Doppler broadening will be the predominant. Therefore, in this video, we have learned about broadening and line shape functions. In the coming video, we will learn about type of lasers. Till then, goodbye.